I was going to say myself that I'm not the Berestycki you think I am. Thank you very much for the invitation to the organizers. And I'm extremely sorry not to be in person with you for this really exciting meeting and occasion to meet friends and colleagues. So hello to everyone, and sorry not to share in presence this meeting. So another thing I wanted to say is, please ask questions or interrupt me. It's really difficult to do this online, so the more you interrupt me, the better it will be. Definitely, so please go ahead and interrupt me if you have something. So I would like to tell you about a theme which is a question, really a general question, which is a question of uniqueness for steady states reaction-diffusion equations in general domains. So first of all, okay, so let's go on. So all this is joint work with Cole Graham, whom I believe should be in the room somewhere hiding. So if you have any difficult questions, please ask him. And likewise, if you want to register any complaint, please register it with him. So it's really ongoing work with Cole. We've been working on this question, and it's quite fascinating because at the beginning we thought it was fairly straightforward question to ask, at least maybe not to solve, but to ask. And the more we go into it, the more we delve into it, the more we find questions and conjectures and surprising behaviors. So stationary states of reaction-diffusion equations. So I'm going to talk only about these homogeneous reaction-diffusion equations, which do not depend on the state, on this point in space or in time. So it's this equation dtu minus Laplace u plus f of u. And I want to discuss these equations in general domains of Rn. So, and so therefore boundary conditions will play a major role here. We are interested in stationary states, that is solutions of the semi-linear elliptic equation, which is one of the simplest nonlinear equations we can think of, which is minus Laplace u plus f of u. And I will always be interested in bounded positive solutions of this equation. Real positive, even if I don't mention it, I always mean bounded positive solutions of this equation. And of course, there are many different types of terms F. We have already seen quite a number of them this morning. And there are also very different boundary conditions that I mainly talk here about Dirichlet conditions, so we use zero on the boundary. But of course, in modeling, in particular in population dynamics, Neumann conditions are important. And likewise, when we be interested in Robin type conditions, or sometimes called third kind conditions, boundary conditions of the third kind, which is rho d the outward normal derivative of u plus 1 minus rho times 3 is equal to 0, where rho is in 0, 1, and rho is equal to 0, we have Dirichlet, rho equals to 1 is normal. And there's an intermediate range of Robin conditions. So the general question I want to ask here is, when you consider a certain domain omega, a certain reaction term F, and we fix a certain boundary condition, when is it true that the positive stationary solution is unique? And I'll try to motivate this for in a minute. So what are the classical types of reaction-diffusion, of reaction terms? Sorry. So since we look for solutions between 0 and 1, you can think of F as defined in 0, 1, just a normalization. F is C1. And I will always assume that 0 and 1 are stationary states, constant stationary states. So F of 0 is equal to F of 1 is equal to 0. So here are the types of F we want to consider. We want to consider bistable F, positive, I'm going to say this in a minute to be more specific. And positive F has several subcases of general positive F, KPP, of weak, strong. And as you will see, the results are obtained according to the type of F we consider, the type of boundary condition, and the domain types. And I will explain this in a minute. So here are the type of functions I want to consider. So what is a bistable F? F is a bistable if F is negative to start with between 0 and some value theta, is positive between theta and 1, and vanishes at 0, theta, and 1. So there are two stable solutions of the ODE, for instance, which are 0 and 1, and one unstable one, which is theta. And for instance, in Lenya's talk earlier today, you heard him mention such terms as the Allen-Kahn equation, which is a particular case of a bistable linearity. In Jason's talk, just before mine, he mentioned Allais effect. So this is typically what is called an Allais effect, where the equation, when the density is too small, is below theta. In fact, the reaction term is adverse to the growth. It actually goes against the growth of u. And if u reaches a certain threshold, then the reaction produces more u. So this is called the Allais effect, and it's also called strong Allais effect. There's also something called the weak Allais effect, which for positive f, in particular when f at the origin is flat, not like that. And you here, when f at the origin is small, this is called weak Allais effect. So it's positive f for me. When I say positive f, is a general f, which is positive of 0, 1. And I will always assume that f prime of 0 is positive and f prime of 1 is negative. There are reasons to consider sometimes the extensions of this assumption, in particular in combustion. Sometimes you want to consider f to be 0 on some interval starting from the origin. So it's not in this framework, but it's closely related, of course. So those are the bistable and general positive f, and now positive f is declining into several subcategories. And I want to distinguish here between what I would like to call the weak KPP assumption. KPP stands for Kolmogorov, Petrovsky, Piskunov. And Lenya, that's the condition that Lenya wrote earlier today. It's that f of s is below than f prime of 0 times s for any s in the interval. So the graph of f lies below its tangent at the origin, and I would really want to have a strict inequality here, really. And what I like to call strong KPP, which implies this one, the previous one, it's a stronger assumption that says that if you look at the intercept of the curve, the graph of f, by lines coming from the origins, and as you lower the angle, the intercept goes up. If you want. To be precise, the ratio f of s, the slope of this intercept f of s over s, decreases with s. So this is what I call the strong KPP. Someone said today earlier that it's convex, it's actually concave. That's what we mean. Basically, you can think of this as concave, but the exact condition we use is this one, slightly more general. So let me tell you why we think about uniqueness. So first of all, let me recall classical results in bounded domains and equations in our head. So for strong KPP, like the one I wrote before, if you look at bounded domains, then if you look at this equation, minus Laplace u plus f of u and u positive in omega with direct boundary condition u equal to 0 in the omega, if you assume that f is strongly KPP, which is the condition I wrote on this slide, then if omega is bounded and smooth, let's say, when it exists, the positive solution u is unique. This is in fact something we prove among many other uniqueness and exact multiplicity results in one of my very early papers. And let me give you, so this is, by the way, this is also true for Robin conditions, actually, for Robin condition, but for Neumann condition, you can be more general. It's going to be true if you assume f to be positive, only to be positive in the way I wrote it earlier. You will see that this is not true for derivative condition. So here is the proof. The proof is very simple, but I like this proof because it explains a lot of things on how one uses maximum principle in these frameworks. So first of all, if you have two solutions, then I claim that you can always pick a very big multiple of one of them, let's say v, and so that it lies above u. There is a large constant k, but u is less than or equal to kv. You need to prove that, for instance, this really relies on the fact that by Hopf-Lemma, the outward normal derivative of u on the boundary and of v on the boundary are strictly negative. And otherwise, if v, for instance, had a flat derivative at some point, and u had a positive one, you could not do that. So it requires this proof. It's quite simple. Then what you do, you start lowering this constant k to reach the best level you can while keeping the condition u less than or equal to kv. So let me call k star the smallest possible value so that u is less than or equal to kv. And my claim is that k star is less than or equal to 1. So to prove this, we argue by contradiction and assume that K star is larger than 1. Then if you write down the equations that K star V minus U satisfies, K star V, of course, minus U is greater than or equal to 0 because we obtain it by continuity from this condition here. But the equation, what you write here, I don't know if you see my pointer. Do you see my pointer? S Laplace of K star V minus U is equal to K star F of V minus F of U. And that's here, that's the point exactly where you use the strong KPP condition. To say that this term K star F of V, when K star is bigger than 1, K star F of V is actually larger than F of K star V, right? Just write F of K star V divided by K star V is less than F of V over V, which is the same as writing K star F of V is bigger than F of K star V. That's the only place where we use the strong KPP assumption. But once you have done that, then you obtain that the minus Laplace of this function here is greater than this difference of functions times K star V minus F of U. And this you can always write as some function Q of X times K star V minus U. You just divide by K star V minus U equals this Q of X, and you multiply by K star V minus U. Right? So the fact that you can write this as a constant term, as some constant coefficient, well, not constant, coefficient depending on X, 0 order coefficient times K star V minus U, is where you use this assumption. Now, of course, you don't know what the sign of Q of X is, so in general, you cannot use the maximum principle. But here, you already know the sign of the function. K star V minus U is greater than or equal to 0. So since it's not identically 0, and it cannot be identically 0, then you know that, in fact, the strong maximum principle applies. Right? Even when you don't know the sign of Q, as soon as you know the sign of the function, then the strong maximum applies. So either K star V minus U would be identically 0, which is not the case, or it satisfies those two conditions. K star V minus U is positive omega, and the outward going normal derivative K star V minus U is negative on the omega. Remember, K star V minus U vanishes on the omega, and again, this is a result of this differential inequality. Minus Laplace K star V minus U minus Q of X, K star V minus U greater than 0. Then, if this is true, by the same trick we used in step 1, we can always squeeze below K star V minus U, we can always squeeze a small multiple of V. In other words, you can pick a very large multiple of K star V minus U to lie above V. So if you it's the same as saying that you can squeeze a small multiple below K star V minus U. But then you get K star minus delta times V minus U positive, which is, of course, a contradiction to the definition of K. Because the smallest K you could find where such an inequality was true. So therefore, what you get from that is that this assumption K star bigger than 1 cannot be held. And therefore, K star is less than or equal to 1, which implies V larger than or equal to U. V larger than K star V, larger than U. But of course, once you have proved that whenever you have two solutions, the second one is above the first one, then you have proved uniqueness. So this is how you get uniqueness. And we see this way of using the maximum principle to try to use inequalities all the way to the optimal value is really what lies at heart of many of the methods resting on the maximum principle, like moving plane method and so on. We mentioned them later on. So let me say a few remarks about this. First of all, I didn't mention existence. Existence is simple. In this framework of one can prove that there is a necessary and sufficient condition for existence, namely that the principal eigenvalue with direct recognition for minus Laplacian operator in omega is less than f prime of 0. So this is necessary and sufficient if you assume that f is a strong KPP type. The second thing I wanted to say is that, in fact, nowhere did I use the structure of the Laplacian. I just used the strong maximum principle. This is true for general elliptic operators. So, in fact, the same result is true for this equation, where you have a uniform elliptic operator, let's say ijx, and you have any first order terms dix, diu, cosine of xu. So this is true in this framework. And in fact, from this, let me just say right away that from this, we can see that extensions to unbounded domains cannot be straightforward, because here we get for free that any equation of this kind has a unique positive solution. However, in all of R, if we look at the equation minus u double prime, it's like minus Laplace u, right? But you just add minus cu prime, the first order term, like I did here. Then this equation, as soon as c is larger than or equal to 2 square root of 0, you get traveling waves. Again, this was mentioned by Lenya earlier. You get traveling waves. And traveling waves, so you have many solutions to say now. You have u equal to 1, which is a constant solution. Then you have traveling waves, and traveling waves, in fact, is one parameter solution, since you can translate that. So there is no hope. So you see that extending this to unbounded domain requires care. Let me come back to bounded domain. So the unbounded condition, in fact, is more general. It's very simple to prove. So if you take the general positive type F, so F is strictly positive between 0 and 1, then the only non-negative solution is u equals 1, aside from u identity 0, of course. And you just work with the minimum and the maximum of u if you want to. You possibly define beyond 1. And you prove that simply analyzing the equation of the minimum and maximum, you prove that u is identical. Very simple. Now, you can think that, okay, so this tells you that for the Neumann problem, we have uniqueness for general positive case, so you might be tempted to say, okay, maybe I was clumsy and I used the wrong proof uniqueness for the Dirichlet condition. That's not true, because for Dirichlet condition, in any bounded domain you pick, you can find some positive f for which there are multiple solutions. So there's no hope to prove uniqueness in a bounded domain for positive f without in general. So, and I'm going to show you this in a minute. So, what is the situation in Euler space? So, in Euler space, there are no boundary conditions. And for positive reactions, that again is true more generally, not for strong KPP, but for positive reactions, just assuming f prime of 0 is positive, there is only one bounded positive solution of this equation, namely u identity 1. So, the proof, let me just sketch it rapidly. What you do, you pick a principal eigenfunction of the Laplacian, and you consider it in a ball with large enough radius r. So what you do is that this allows you to construct, look epsilon phi r, you construct a one parameter family of solutions, of subsolutions of your equation. Because you see this, if you take epsilon phi r, this is going to be less than f prime of 0, f prime of 0 over 2 if you want. So if you compare this with f of epsilon phi r, on one hand you have f prime of 0 epsilon phi r, more or less, and on the other hand you have something smaller, so you have a one parameter family of subsolutions. This allows you to say again that u is going to be above epsilon phi r for all epsilon between 0 and epsilon 0. The reason is that you start, u is positive. You can prove that if u is not identity 0, u is strictly positive. So if you look on a compact ball, then small enough epsilon phi r is below the solution. And then you let epsilon rise. And because epsilon phi r is a subsolution, and because on the boundary it's 0, so it never touches at the boundary. The first place it could touch you would be an interior point. But a solution cannot touch from below a subsolution unless they are equal, which is not the case here, of course, because subsolution vanishes on the boundary of the sphere. So this means that you can go all the way up to epsilon 0, that is, as long as you keep epsilon phi r to the subsolution. So this tells you that Q of 0 is above epsilon 0. Let's say we assume we normalize phi r to be 1 at the origin. And then what you do, you repeat this argument by moving the ball around. You do it at 0, but nothing tells you that 0 is a particular point of interest. You can do the same argument at any point in space, and then you get that u is bounded away from 0 by epsilon 0. And then when you look where u achieves a minimum, including possibly at infinity, and to get where x bar, where u of x bar is the minimum. So either it's reached at the final point, or you have to follow a sequence going to infinity, translate your functions u, so that the translate is always the xn, it's always the origin. And then in the limit, you can pass to the limit with standard elliptic estimates. And you get a solution where u reaches its minimum strictly positive. since the equation is minus Laplace u of x bar to f of u of x bar, if u of x bar were below 1, then f of u of x bar would be strictly positive. So you cannot have a minimum minus Laplace u be strictly negative. So therefore, this tells you that u, the minimum of u is 1, whence u is identically 1. Okay, so this is the gist of the arguments in this case of bounded domain in one of R. So you see the difference between the two cases, right? In Rn, just enough to have positive, and in the bounded domain, you require strong KPP for this. So let me go now and look at bounded and unbounded. So the question is, so we have just seen a theorem in all of space. We have just seen also a theorem in bounded domains. Can this theorem in bounded domains be extended to general domains? So we're going to look at KPP reaction terms. So this is the question, what about general unbounded domains? So I want to understand how this can be extended. I'm going to consider a case of strong KPP type. So I hope that I'm allowed to have injury time, right? So to the result we cannot get in general, we have to have a kind of non-degenerate system. It's very general, but not quite the full generality, but it's nearly there. And let me describe to you what we mean by this. So for this, I need to introduce the notion of generalized principle directly eigenvalue. This is something we had introduced with Neander and Varadhan, and then we took the same approach with Luca Rossi to discuss this notion in unbounded domains. So here's the definition. So we define lambda 1 of the operator minus L, and is an elliptic operator, to be the supreme of lambdas for which you can find a positive super solution. Okay, so L plus lambda equal to 0 is the eigenvalue equation, if you want. And we define lambda 1 to be the supremum of the lambda for which there exists a positive super solution of the eigenvalue, eigenfunction equation, which is here. That means it's a super solution. And you can prove, so there's a lot of properties we study here, but in fact, this is has many nice properties, in particular that lambda 1 is the limit of the principal direct eigenvalues of minus L if you take the intersection of omegas with all of previous R and you let R go to infinity. Some property like that was already observed by Schmidt-Agman. So here's a proposition. Remember, in the bounded domain case, we had the necessary and sufficient condition expressed in terms of the principle for existence, same person in terms of the principal direct eigenvalue. So here is a proposition. This is true for weak KPP. Weak KPP means a graph below the tangent. The equation that needs a positive solution if this principal eigenvalue is strictly negative. And conversely, there is no positive bounded solution if we assume that lambda 1 is strictly positive. So it's very much like the bounded domain case. If you use this notion lambda 1, which I just introduced, which you have to note another notion, and just the difference with the bounded case is that the critical case where here it remains open, lambda 1 equal to 0, we don't know. We conjecture that it is the same as in the bounded domain case, namely that when lambda 1 is equal to 0, there is no positive bounded solution in this case. And I should mention that this is really analogous to results we have obtained in our discussion of equations in all of Rn, but with variable coefficients. This is some paper with François Hamel and Luca Rossi. So to discuss now the question of uniqueness, we need to introduce some notions. And here are the notions we want to use. We're going to say, given some number mu, we're going to say that the domain is mu narrow if the principal eigenvalue of minus Laplace minus mu is strictly positive. And likewise, we're going to say that it is mu ample if, so we require it a bit more seemingly, that lambda 1 of minus delta minus mu, not only omega, but omega star for any connected limit of omega star of omega, I'll explain what this means, is strictly negative. So that means, okay, so mu narrow is the principal eigenvalue lambda 1 is positive, mu ample means that it's negative, not only for omega, but we want to do that in some sense all the way to infinity in any possible direction you go to infinity, you have the same property. So what do we mean by that? We mean if you take a sequence of points going to infinity, you translate omega by these points, and you can strike out a subsequence where you have convergence. And what we mean by connect means you pin down, you look at the components so that one point is pinned, it contains the origin itself. And what you do is you take the component that contains 0. That's what we call. So we want to have it for every such direction. So, okay, first of all, so why do we call it mu narrow? So this, in general, what this notion tells you is that there's a balance between, on one hand, the mu growth in the interior and the fact that the Dirichlet condition at the boundary tells you that there is absorption at the boundary. So there is a balance between those two things. And if lambda 1 is positive, it tells you that the boundary effect is more important. In fact, every point has to be relatively close to the boundary in this domain when you have narrow position. And so that's why we call it narrow, because every point in some sense has to be relatively close to the boundary. And ample, in fact, what you say by ample is that you don't want that, but you say that the domain is sufficiently spacious, not only at finite distance where you look at, but at infinity also in this sense that we find here. In fact, the first condition can be phrased in the same way. If it's strictly positive, then it will have also every limit in connected components will also be positive. So in fact, those two notions, ample and narrow, are quite symmetric in spite of what it looks like. If you have any questions, don't hesitate. Right? Okay, so here is the result for uniqueness in general domains. So here's our result, the best we can prove at this point. Suppose that F is of strong KPP type, and that omega can be written as the union of an F prime of 0 narrow and an F prime of 0 ample smooth open set. Then when it exists, the positive bounded solution of the equation is unique. So as soon as you can decompose, the decomposition is by naming unique, of course. So as soon as you can decompose omega into the union, overlapping union ample set and narrow F prime of 0 ample and prime of 0 narrow, then you have improved uniqueness. Now, of course, this begs for the conjecture that is here, which is, again, there are many open points in this theory, as you will see. But here is one which is very natural. The conjecture would be that if you take a general domain, assume that the domain is uniformly smooth if you want, if F is strongly KPP, then the equation admits at most one positive bounded solution. It's a very natural conjecture, true in our N, true in bounded domains, and true in these domains which actually are very general. So let me tell you what this entails, this condition. So ample domains, I have shown you examples of such ample domains. If you look at strips, the domain will be ample if the width of the strip in dimension 2. So a tube would involve the principal eigenvalue Laplacian to transverse domain. But let's rewrite it from the sake of simplicity in dimension 2. It will be ample if the width is larger than pi over the square root of F prime of 0. And F prime of 0 now if this height, this width is less than pi over the square root of F prime of 0. So it will be critical when H is exactly equal to this. And if you look at what can happen, what can go wrong, it's exactly happening in domains like that. So I like to call these domains the infinite light bulb. Infinite light bulb. So you take a domain, for instance, which is ample, and then it's followed by strip in dimension 2, or generally cube. And the non-degeneracy simply means that if you assume that it's straight, that H is not this magic number. So you see, it's true for all H, except possibly for this. I should say that in score we have an argument, very slick argument to discard also possible solutions in this critical degenerate case, but it's formal at the moment. So it's probably true in general, criticalness. Here, let me give you other examples. So the domain omega is here. I like to call infinite comps. So you have a domain omega, and you have teeth of the cones that go out all the way to infinity here. And let's assume that they are straight, past a certain values are straight. So the non-degeneracy condition would be simply that the infimum over I of the HI inspired with square root of n will be strictly positive. So this is non-degeneracy condition. So you see that domains we miss are really quite particular, but nevertheless the argument breaks down. And even the proof is not so straightforward when it's to dealing with infinity is always complication. Let me skip this. So this was the proof of necessary and sufficient conditions, almost necessary and sufficient conditions. Let me tell you about Neumann conditions. So for Neumann conditions, in fact, if you again we can prove a general result for positive type with f prime 0 positive. Then the result just positive because f prime 0 positive. The result is that U is identical to 1 is unique positive bounded solution in Neumann condition. So it's more general than the Dirichlet condition. And we can prove this when you assume uniform regularity of the domain omega, and we conjecture the same result should hold for any domain which is locally simple. But at the moment we use this uniform regularity in our argument. Okay, and this again is a rather involved argument. So straightforward, you always have to deal with ruling out points, minimum, maximum occurring at infinity, and this is part of the difficulty here. So what do we know about positive reaction terms? So what do we know? So I just mentioned something from Neumann, but let me treat now Dirichlet, come back to Dirichlet for positive reaction terms. First of all, I mentioned that earlier. I say that if you look at Dirichlet conditions, on every bounded domain omega, there exists a positive reaction F, which such that the equation with Dirichlet condition has multiple stable positive bounded solutions. In fact, you can even choose this F to satisfy the weak KPP assumption, which is written here. And the same is true for Robin conditions. And for Neumann conditions, you know that it's true in bounded domains. And the proof is this. Okay, let me just show you this drawing. The proof is this. We can find a solution of this equation of bounded domain, which is below this KPP type function f between 0 and 1. So the maximum of the solution is somewhere here, rho, it's below 1, strictly below 1. So nothing prevents you from saying, I'm going to change my function f just after rho here. I take the same f as before, but after rho, before I reach 1, I turn down and I put here a huge lump of mass. And then if you look at the minimum of the energy associated with this mu f bar, you can show that because of this lump, it pays off for the energy to have mass here in this part. Therefore, you have another solution. In fact, that solution is usually above the other one. You can prove it also. You can prove that there is one above the other one. And therefore, you have two solutions here. So you see, it's very different from the Neumann case. In the Dirichlet case, you can easily construct positive solution function, even satisfying the weak KPP, for which you have two solutions. Let me say something about non-unbounded case. So it turns out that if for positive F, you can still, in some domain, for positive F, you can still find regions for which you have uniqueness. And those are what we call, so those are domains epigraphs, which are bounded by a globally Lipschitz function phi. So if you look at domain omega, which is the form xn bigger than phi of x1, etc., xn minus 1, with a global Lipschitz function phi, then the equation has unique positive bounded solutions. This is something we proved way back with Staffarelli and with Nielber. We proved that solution is increasing in xn, mu of x goes to 1, as a distance from the graph goes to infinity. So there is, you see, so it's very surprising that if you just take F positive and you allow the domain to be bounded by Lipschitz graph to be an epigraph, then you don't have this strange phenomenon of having two different solutions. In half space, you can prove in the same way, for the positive case, that in a half space, well, there is previous result, because it's a Morgan graph in many different directions, you can prove that the solution is actually unique in half space and is a function of xn alone. So there is a one-dimensional symmetry result, which is also true, and we proved it for positive F in that paper with Caffarelli. Now, what can we prove for general equation? Can we prove something for general equation, general F? So let's consider the half space in R2 or R3. And so in half space, like this one, R2 plus or R3 plus, and with direct conditions. Then we showed with Caffarelli number, we showed that in this case, all positive solutions are one-dimensional, namely that Q is equal to F of Xn, and therefore use the solution of the ODE, and you can prove that it is unique. So this is a result. In particular, if F is bistable, ignition of positives, and the equation is unique by the coefficient. You need to add some conditions to avoid multiple oscillations and things like that. But nevertheless, so in this case, for quite general F, you have solutions. Okay. What about higher dimensions? So this seems to be completely open. It's really surprising because it's very much related to celebrated the Georgi conjecture, and I don't have time to go into this. But for the Georgi conjecture, it's known that in higher dimensions are counterexamples. It's related to the theory of minimum surfaces, and in fact, there are minimum surfaces in high enough dimensions which are singular. But for this equation, it's not known, and it's really very, very strange. So the only result there is here is that in general, right, in general F, not in positive F, I just mentioned it before, but in general F, is it this true or not? It's not, or is it true up to a certain dimension, for instance? It's a natural conjecture. Nothing wrong. So let me go about the Robin condition and saying that this is not true, even in dimension 1, and with core we were able to, we're really interested in some other questions, but we were able to prove that there are rows in Fs for which, in bistable F, for which the equation Robin condition has multiple solutions in R+. This is very surprising. You see, there's uniqueness for in bistable case for the Dirichlet condition, there's uniqueness for the Neumann condition, but not for the Robin condition. So things are more, life is more complicated than it seems. So I've mentioned here the outstanding open problem, I already mentioned them. And I should say also that the Neumann condition case in monotone graphs or in coercive graphs or in half space, there's nothing known, basically. It's fully open. Let me conclude, I just have a few more minutes. Let me conclude with something about bistable equations. So bistable equations, specifically, I mentioned them several times already, is this F, which I showed you already before. And we assume here that the nonlinearity is unbalanced. So that is the integral from 0 to 1 of F is positive. So the mass here is above the mass here. It's unlike the example of Einstein that I showed at some point, whereas it's balanced, so the mass here is equal to the mass there. And so to start with, for the bistable equation, what's the situation in bounded domain? Can there be multiplicity? In fact, Paul Rabinowitz showed that multiplicity is the usual situation. In fact, if you put here a parameter, lambda, and you look at this F, which is bistable and unbalanced, then what Paul Rabinowitz proved is that there exists a critical value of lambda star, for which, below which there is no solution, at which there is at least one solution, and above which there is at least two distinct positive solutions, when lambda is bigger than lambda star. And usually the second solution is unstable. There is one which is stable, weak in a weak sense. And he proves that, Paul proves this with using topological degree argument. It's one of his early results as well. So the rule in bounded domains is that bistable nonlinearities will have unique solution. And you can construct, I won't have time to discuss this, you can construct stable multiple solutions in unbounded domains by blocking phenomena in domains in this way. When you take a narrow connecting, you can construct solutions which are going to be big here and small there, and vice versa. So it will block the invasion of the. So there are multiple stable solutions. But in a Lipschitz epigraph, it's not the same thing. So suppose suppose that you look at this equation in a Lipschitz, global Lipschitz function epigraph, an epigraph defined by global Lipschitz function phi, and you want also to know that this is yeah, I meant to say that it has to be coercive, this graph, and so it has to be coercive. I forgot a condition here, and in fact, respect to several directions. Then the equation is positive, has a unique positive solution. And this solution is strictly increasing in n and goes to 1 as a distance from the p omega goes to infinity. In fact, if you apply this to an Can, like the one that Lena showed earlier, I just added this after listening to his talk. In fact, we can also treat the Can equation, but then the conclusion of this is that if you have a Can condition with a balanced bistable term, then if you have phi global Lipschitz and this coercive condition, then the equation does not have a bounded positive solution. And also the same would be true in dimension n equals 2 or 3. And the reason being that if you have a bounded positive solution, defined for the Can or any solution of that kind, nothing prevents you from changing the f way after the maximum of u. And then you change it and you make it bistable nonlinearity. Therefore, if you have a theorem that says any solution of the bistable equation has to go to 1 at infinity, then you know that's not going to be true for solutions like that. Okay, so in the Can cannot go to 1, and that's another result that you can put. Now, if you consider a cone which is included in a circular cone of opening angle less than pi over 2, then for the bistable case, the equation is direct definition has unique one.
So you should finish in about 1 to 2 minutes.
Okay, so I'm done. This is really extremely good timing. So as a corollary, I just wanted to say that the unique solution, if you look at what we call a scalar field equation, minus Laplace u plus u equals u to the p, if you look at such solution, a cone with or ellipsis epigraph containing such a graph and containing such a cone, I mean, and with direct condition, then there is no bounded solution of this. The reason again being that this, if there was a bounded solution, you can turn it into a solution of a bistable nonlinearity. It will have to go to the second zero, stable zero of f. So you don't have that. So you get this. We have many conclusions of this type. So to finish, I'll just say that I like this theorem because it uses both for those specialist moving plane method where we use Alexandrov and Serin's method of moving planes. And we also use sliding, that taking the domain, sliding it upwards and bringing it down after something. So thank you very much for your attention.
There are questions. I mean, I have a very naive question. So where do these different domains actually pop up? And I guess there's a motivation from physics, but so what are people actually interested in which type of domains?
So for instance, to understand the question, we just give you. So there are many reasons why you want to consider domains in all modeling situations. Okay, if you want in physics in the scalar field equations, which I mentioned, one would like to construct solutions that would be positive in a quarter plane, negative with certain symmetries, negative in another quarter plane, positive symmetry, etc. And what this one of the upshot of this, what I mentioned here, is that there are no such solutions. There are no solutions that are bounded. You can hope to find some which are unbounded, but you won't find some which are bounded. So if you want to find what is called bound states, so not positive solutions, you probably look at radial solutions which have oscillations. That is, there still are radial symmetry, but oscillate. So that's one of the consequences. In the population dynamics, you often want to understand the consequences of geometry where there is a narrow corridor to cross for an evading species, for instance. And it's very natural to look at the effect of such a corridor, whether they can pass or not, or whether it's opening or not opening. And our results show and in other problems in biology, like propagation, so the propagation of depolarization waves in the brain, there are models which are exactly with that bistable, where you would like to understand when it's blocked or not blocked. So this all shed light on this. What is the effect of the geometry? It's a general question if you want to understand both in population dynamics and in biological modeling.
I think there's also a question by Pascal.
Yes, thanks, Henri, for the very nice talk. I have a question about the strong FKPP case. So in the case where the nonlinearity is amenable to analysis through branching Brownian motion, so say u times 1 minus u. So I guess then for the elliptic equation, so it's the probability that this branching process survives. Yes, well, at least if it's unique, then it should be this one. So has this been tackled by probabilistic methods?
No, in fact, that's an excellent question. In fact, I was hoping to whet your appetite, you probabilists who are present in the room, because it calls for a probabilistic approach. You see, for instance, in the Neumann case, it's very natural to imagine that there is no absorption on the boundary. So you imagine that every point, eventually you will get one, right? But so at this point, we were able to prove it, but we had to assume that the domain is uniformly smooth. Now, okay, not uniformly smooth is a bit strange, but I confess, but nevertheless, technically we can prove it with analytical method at this point, but presumably probabilistic method would be able to show that. So that would be very interesting thing to prove. Now, if you look at Dirichlet conditions, and of course it's a bit more complicated, and Dirichlet conditions may, okay, so you have absorption, and you have to measure the absorption against the other, and maybe, but still one could perhaps prove that once there is invasion, then the only possible finding state should be one. Maybe probabilistic method would be very interesting to have both approaches, for sure.
Are there any more questions? Maybe there is one online, I'm not sure.
Oh yeah, there is one question in the chat. Thanks for you, by Truong Wu. The condition F, so that F vanishes at 0 and 1 seems to be restrictive. Is it possible to relax this condition? Can we characterize the corresponding results in terms of F?
Okay, so this is a proof of what Louis Nierenberg once told me, that mathematicians are greedy. So you tell them what you think is a nice theorem, they always want to know more. So it's true, it's a good question. In fact, some of our results in half space and so on can be obtained in half space, or can be obtained with F under certain sign assumption of 0. F of 1 has to be there because that's the only way you are going to be able to say something about what is, I mean, you can say something that F is strictly bounded from below by positive constants, and there won't be solutions. So this is uninteresting. But you may, and usually what you want to say is that F of 0 is not 0 and F of 1 is 0, you have something. So there are some results in half space and Lipschitz domains, but at this point, there are no results for general domains, I would say. It's a good question, it's a very good question. But there are some results. Denser also had some results in half space, Norman denser, and there are some results also.
So I think there are no further questions. So we can thank all speakers of this morning and actually of the day.